Scientists have made a key discovery about antimatter, a mysterious substance which was plentiful when the universe began. Antimatter is the opposite of matter, from which stars and planets are made. Both were created in equal amounts in the Big Bang, which formed our universe. While matter is everywhere, though, its opposite is now fiendishly hard to find. The latest study has discovered the two respond to gravity in the same way. For years, physicists have been scrambling to discover their differences and similarities, to explain how the universe arose. Discovering that antimatter rose in response to gravity, instead of falling, would have blown apart what we know about physics. They've now confirmed for the first time that atoms of antimatter fall downwards. But far from being a scientific dead end, this opens the doors to new experiments and theories. Does it fall at the same speed? For example, during the Big Bang, matter and antimatter should have combined and cancelled each other, leaving nothing but light. Why they didn't is one of physics' great mysteries, and uncovering differences between the two is the key to solving it. Somehow matter overcame antimatter in those first moments of creation. How it responds to gravity may hold the key, according to Dr. Danielle Hodgkinson, a member of the research team at CERN in Switzerland, the world's largest particle physics laboratory. We don't understand how our universe came to be matter-dominated, and so this is what motivates our experiments, she told me. Most antimatter exists only fleetingly in the universe, for fractions of seconds. So to carry out experiments, the CERN team needed to make it in a stable and long-lasting form. Professor Jeffrey Hengst has spent 30 years building a facility to painstakingly construct thousands of atoms of antimatter from subatomic particles, trap them and then drop them. Antimatter is just the coolest, most mysterious stuff you can imagine, he told me. As far as we understand, you could build a universe just like ours with you and me, made of just antimatter, Professor Hengst told me. That's just inspiring to address. It's one of the most fundamental open questions about what this stuff is and how it behaves. Let's start with what matter is. Everything in our world is made from it. From tiny particles called atoms. The simplest atom is hydrogen. It's what the sun is mostly made from. A hydrogen atom is made up of a positively charged proton in the middle and negatively charged electron orbiting it. With antimatter, the electric charges are the other way round. Take antihydrogen, which is the antimatter version of hydrogen, used in the CERN experiments. It has a negatively charged proton, antiproton, in the middle, and a positive version of the electron, positron, orbiting it. These antiprotons are produced by colliding particles together in CERN's accelerators. They arrive at the antimatter lab along pipes at speeds that are close to the speed of light. This is much too fast for them to be controlled by the researchers. The first step is to slow them down, which the researchers do by sending them around a ring. This draws out their energy until they are moving at a more manageable pace. The antiprotons and positrons are then sent into a giant magnet, where they mix to form thousands of atoms of antihydrogen. The magnet creates a field, which traps the antihydrogen. If it were to touch the side of the container, it would instantly be destroyed, because antimatter can't survive contact with our world. When the field is turned off, the antihydrogen atoms are released. Sensors then detect whether they have fallen up or down. Some theorists have predicted that antimatter might fall up, though most, notably Albert Einstein and his general theory of relativity more than 100 years ago, say it should behave just like matter, and fall downwards. The researchers at CERN have now confirmed, with the greatest degree of certainty yet, that Einstein was right. But just because antimatter doesn't fall up, it doesn't mean that it falls down at exactly the same rate as matter. For the next steps in the research, the team are upgrading their experiment to make it more sensitive, to see if there is a slight difference in the rate at which antimatter falls. If so, it could answer one of the biggest questions of all: how the universe came into existence. The results have been published in the journal Nature.